Question 27. The graph of y equals f of x, where f of x equals a times the absolute value of x minus b plus c, passes through the points 3, -5, 6, 7, and 9, -5 as shown in the diagram. Part A. Find the values of a, b, and c. The graph of f of x is the graph of y equals the absolute value of x that's been translated to the right-hand side. It's been reflected in the x-axis, so it's an upside-down v, and it's also been dilated or stretched vertically. Now the question is asking for the values of a, b, and c. Now I think at this stage the easiest value to find is the value of b. Let's go back to the function definition. We have f of x is equal to a outside of x minus b in absolute values plus c. So the value of b would represent the horizontal translation. Now the x-coordinate of the vertex has moved from the origin to 6. And that's given by the x-coordinate here. Hence, b equals 6. Now referring back to the vertex, the y value is 7. In other words, f of 6 equals 7. Now we know the value of b, it's 6. Now if we substitute x equals 6 into f of x, we'll get 7. So substituting those values into the function, we can then find the value of c. So 7 is equal to a times the absolute value of 6 minus 6 plus c, and the absolute value of 6 minus 6 is 0, and 0 times a is 0, and that's why c is equal to 7. Now the last thing we need to find is the value of a. And if we choose any point other than the vertex, so either this point here or this point here, and substituting those values for x and y into the function, we can then solve it for the value of a. So f of 3 is equal to -5, and that comes from this coordinate here. So substituting x equals 3 for x and -5 for f of x, we get -5 is equal to a times 3 minus 6 in absolute values plus 7. And the absolute value of 3 minus 6 is positive 3. So -5 is equal to 3a plus 7. Subtracting 7 from both sides to make 3a the subject, we get 3a is equal to -12, hence a is equal to -4. Therefore, a is equal to -4, b is equal to 6, and c is equal to 7. Part B. The line y equals mx cuts the graph of y equals f of x in two distinct places. Find all possible values of m. To help with the explanation, I've drawn two lines passing through the origin. The line y equals m1x, which has gradient m1, and the line y equals m2x, which has gradient m2. Now the value of m must lie between m1 and m2. Notice that y equals m1x passes through the vertex of y equals f of x. I'm just going to demonstrate this with a ruler. So if I place the ruler on the origin, superimposed over the line OE, or y equals m1x, if I move the ruler clockwise, we can see that it intersects with the graph at two distinct points. So if I move it anti-clockwise past the vertex, clearly it does not intersect the graph at two distinct points. So the line y equals mx must have a gradient less than m1. Now if we consider the gradient m2, at the moment I've drawn y equals m2 parallel to EF, which means that the line y equals mx must have a gradient greater than m2. Now if I turn the ruler anti-clockwise, we can see that it intersects the graph at two distinct points. So if I move it back here and move it the other way, we can see that it would only intersect the graph at one point. So let's work out the gradient of M1. Starting at the origin and passing through point 6, 7, using rise over run, it's going to be 7 over 6. So the first point we could make is that the gradient M1 must be less than 7 over 6. Now, I made the point earlier that the gradient of y equals m2x must be greater than the gradient of EF. So this is EF here, and the gradient of this line, which at the moment is parallel to EF, it must be greater than the gradient EF. And we can work that out using the gradient formula, y2 minus y1 divided by x2 minus x1. So the gradient of EF is equal to negative 5 minus 7 in brackets. So that's y2 minus y1 divided by 9 minus 6 in brackets. So that's x2 minus x1, rise divided by the run. And that gives us negative 4. Therefore, m must be greater than negative 4 and less than 7 over 6.